All right, welcome. Some announcements for you all. Just don't forget your chief homework is due Monday, and then our midterm is next Wednesday. So we'll meet in class on Monday. I have office hours on Tuesday, and then our midterm will be on Wednesday. It is all multiple choice. I will provide your Scantron. Just make sure you bring your non-graphing calculator and a pencil to fill that in. And then keep in mind that it is cumulative. So we covered chapters 11 through what we're covering today in chapter 14, and that's fair game for the assessment. I opened up the learning curves for chapters 13 and 14. So 11, 12, 13, 14 are all available for you all. If you complete them, they're due the Monday after the midterm. They are a good study resource for the midterm. There are a bunch of multiple choice questions about the content in those chapters. So I make them available for you, of course, before the exam, but they're not due until after because I didn't want anyone stressing about completing it the night before, right? Like you can use what's useful for you for studying for the midterm, and then just keep that in mind that they'll be due a few days later if you want the extra credit. So completing one, reaching the target score for that learning curve will add 1 point to your midterm, or unit exam 1, whichever grade is lower, I'll add the extra credit to. We'll post reminders about that and the midterm as well. All right, I think that's all questions about logistics. Okay. Towards the end of class, we started talking about the integrated rate law. Remember, this is useful when we're thinking about the concentration of a reactant over time. So as a reaction progresses, reactants are used up. You need a reactant to form a product. So if you're doing a reaction, the reactant is being used up in forming the product. Having less reactant present will decrease the reaction rate. We talked about how increasing concentration can increase reaction rate. With the integrated rate law, this is for a first order reaction. We can calculate, if we know the rate constant, how much time has passed, the initial concentration, we can calculate that concentration at time t. We also can rearrange it into this y equals mx plus b version. The only difference here, these two things will calculate the same way. Remember that if you have a fraction, a natural log of a fraction, this is equal to natural log of the top minus natural log of the bottom. And then we just added the numerator or the denominator to the other side. We'll do that in one of the problems today. So that's for the first order reaction. Then we talked about half-lives. A half-life is the amount of product, or the amount of time rather, that it takes to use up half of the initial concentration of the product. So that's the definition of a half-life. For a first order reaction, that time is only proportional to K. It's not proportional to the initial concentration, but that time is equal to natural log of 2 divided by K. So now we'll think about second order reactions. So we'll talk about integrated rate laws for first and second order. We won't go into third order reactions. But remember, a second order reaction, a reaction that's second order with respect to one reagent has that rate law. equal to K times the concentration of that reactant squared. So we can say that if this is the rate law for a reaction, it is second order with respect to A. There's another possible rate law that is also a second order reaction. And that's when you have two reagents and the reaction's first order to each reagent. So if we say A and B are reactants, reagents mean the same thing. This second rate law indicates that overall this reaction is a second order reaction. It's first order with respect to A, first order with respect to B, so second order overall. So both of those rate laws indicate that whatever reaction they're talking about are second order reactions, but for the integrated rate law, we're only going to focus on that first one where we have second order reaction with respect to one reagent. This is what your book focuses on. The other one is more complicated, and we're just not going to get to that this term. All right, so we're focusing on that one. We have one reagent, and the reaction is second order with respect to that reagent. So the second order rate law, two ways to write it. We can say rate is equal to the decrease in concentration of A over change in time. This is also equal to the rate constant times concentration of A squared. So what we have above. The integrated rate law, which considers time for a second order reaction, is 1 over concentration of A at time t, which is equal to rate constant times time plus 1 over concentration of A at time 0, or initial concentration. The book derives this equation. I'm not going to go through that derivation. This is an equation that's provided for you on the periodic table sheet. And it says, like, it will label which integrated rate laws for they have 0 order, first order, and second order. So this one's listed for second order reactions. If you're interested, or what it helps you understand that equation, if you see the derivation, I encourage you to look at the book. But what we'll do is just focus on how to use this equation. Now, this equation is already written in a y equals mx plus b format. 1 over concentration of A at time t is y. That is dependent on t. So t would be x. It's multiplied by k. So k is m. K is the slope. And then 1 over concentration at time 0. That is a constant. So that will be b, or the y-intercept. So notice the integrated rate law for second order reaction is different than the integrated rate law for first order. The laws depend on what type of reaction order you have. As a result, the equation for the half-life of a second order reaction is also different than the half-life of a first order. So that is, we'll derive it on this next slide here. So remember, a half-life, that is the time it takes to use up half of the initial concentration. We went through this derivation for a first order reaction on Wednesday. We'll do this for second order. We will start with that integrated rate law. One over concentration of A at time t is equal to rate constant times t plus 1 over initial concentration of that reagent. Now if we substitute the definition of concentration of A at time t, we're talking about a half-life. We're talking about the time it takes to use up half of the reagent. So that means at the time of the half-life, after that amount of time, 1/2 of the initial concentration is left over, is what's remaining. So that means that concentration of A at time t is equal to 1/2 times the concentration of A at time 0. So that's what we're substituting in here. So we have 1 over 1/2 initial concentration of A, and then everything else is the same. Kt plus 1 over initial concentration. Now we're looking to have the equation for time, the half-life, which has subscript of 1/2. So rearranging this equation to get time on its own, we're combining these terms, dividing by k. I'm not going step by step, but the half-life of a second order reaction is 1 over k times the concentration of A at the initial time. So this is a different equation than the half-life for a first order reaction. You might remember, or if you look back, the half-life for a first order reaction is natural log of 2 over k. It does not at all depend on the initial concentration. It only depends on k. For a second order reaction, the half-life depends on the initial concentration and k. So let's write that in here. So if you increase k is increased, half-life will decrease. Increase initial concentration, half-life will decrease. They're inversely proportional. All right, let's do this learning check on the next slide. So we are provided some information. We have the rate constant for a first order reaction where A is the reagent. They provide the rate constant. What's the variable for a rate constant? K, yes. So they give us K at a certain temperature. Says if the concentration of A at the start of the reaction is 0.840 molar, what is the concentration of A after 2 seconds? They tell us, this question tells us the concentration of A at the start of the reaction. So that's initial concentration. That's A subscript 0, time is 0. And the question is, what's the concentration of A after 2 seconds? That's our T, our time. Okay, so I'll start the iClicker. The iClicker, there's 2 questions, just asking what equation do you use to solve this part of the question, and then what equation would you use to answer this. So work through it, identify those equations. We'll go through it together in a few minutes. But yeah, so it's just rearranging. Did it work? Oh, okay. It's 30 more seconds. All right, I'm going to close it here. Okay, so we are given the information that this is a first order reaction, and it doesn't ask anything about the half-life, but it does ask for concentration after a certain amount of time. So we need the rate law that integrates time. It's an integrated rate law, and it needs to be for the first order reaction. So there are two ways to represent that equation. We have both of them in our slides. There was only one option for your iClicker, but to start with the fraction in the natural log, that's the natural log of A at time t divided by natural log of A, the initial concentration of A. This is equal to K times T. I'm going to rearrange this real quick to get to the y equals mx plus b version, and that's what was the option on the iClicker. So remember that if you have the natural log of a fraction, this is equal to natural log of the numerator, natural log of A at time t, minus natural log of the denominator, natural log of initial concentration, and all of this is equal to negative K times T. So the y equals mx plus b version, we just add natural log the initial concentration to both sides. And now we can plug in values. We're looking for concentration of A at time t. We've got rate constant, we've got time, we've got initial concentration. So negative 0.690 seconds to the negative first power times 2 seconds plus natural log of initial concentration 0.840 molar. This is negative 1.38 minus 0.174. Going to continue this on the right side. All right, so multiplying seconds together, seconds to the negative first power, negative 1.38. Natural log of this value, negative 0.174. So now natural log of A at time t is equal to negative 1.554. So I just simplified the right side. Okay, so from the equation, y equals mx plus b version to here, we've just plugged in values, multiplied, and subtracted. Now we have the natural log of the variable we're looking for is equal to this negative value. We need this concentration, this variable on its own, not part of the natural log, to cancel out the natural log part of this equation. We raise both sides of, or we raise e to the power of both sides of the equation. So we have e, that's a function in your calculator, to the natural log of concentration at time t is equal to e to the negative 1.554 power. If you raise e to the natural log of something, e and natural log cancel out, and we just have this variable left. So the left side of the equation is equal to concentration of A at time t. The right side of the equation, you can plug that into your calculator. Find the e function, raise it to this value, the power of that value, and the right side of the equation is equal to 0.211, and this is concentration, so molar units. This is another process where we can think about this final answer and if it makes sense, knowing what we know about a reaction. As a reaction proceeds, reactants are used up to form the product. We started with an initial concentration of 0.84 molar. We end with 0.2. This is a lower concentration, so that works. If this were a higher concentration, something would have gone wrong. Questions on this first one? Okay. If this is a second order reaction, because they told us, the question just said this is first order. If they said it was second order, then we have a different integrated rate law that needs to be used. And that is the integrated rate law for a second order reaction. 1 over concentration of A at time t equals KT plus 1 over concentration of A at time 0. I won't go through calculating it, but you can try on your own. And concentration of A at time t for a second order reaction is 0.389 molar. Different concentration because the decrease in concentration of reactants is different if you have a first order or a second order reaction. Depends on the order of the reaction. Okay. Give you all a second to finish writing, and we'll go to the next learning check. Okay. Another question here. Putting these equations to use. This one asks about half-life. So a first order reaction, that tells us some information, has a half-life of 63.4 minutes at 225 degrees Celsius. We are calculating the rate constant. Remember what that letter is? Rate constant, K, for this reaction. And after calculating the rate constant, determine the percentage of the reactant remaining after 25 minutes. So they provide half-life. They tell us it's a first order reaction. You need to solve for K and use that K value to determine the percent of reactant remaining after 25 minutes. I give you all like 3 minutes to get started, and then we'll work through it together. But try at least working on A. Think about what equation you'll use. Maybe think about what equation you'll use for B. Get started on that. We'll do 3 minutes, so 11:29. We'll come back together. Okay, let's go through A and then we'll get to B. So A, we're calculating the rate constant. We have the half-life, and we have the information that it's a first order reaction. So we use the half-life equation for the first order reaction. T 1/2 is equal to natural log of 2 divided by K. So in this equation, the only variable that we don't have a value for is K. That's what we're solving for, so that's perfect. Plug in, well, I'll rearrange first, and then we'll plug in values for time, the half-life, and then calculate natural log of 2, and we'll get K. So K is equal to, just doing rearranging, natural log of 2 over half-life. So this is natural log of 2 over 63.4 minutes. Plugging that into your calculator, K is 0.0109 minutes to the negative first power. Now for part B. The time is 25 minutes. That's not the half-life, so we need to use the integrated rate law here. But also, we don't have initial concentration, we don't have final concentration, we kind of have two variables. But the question isn't looking for one on its own, it's looking for the percentage of the initial that's remaining. So if you have a certain amount of A remaining after some time, that's concentration of A at time t. If we had that value, we wanted to know what the percentage remaining of the initial concentration was, we would divide this by the initial, multiply by 100%. That would tell us percent of A remaining, or percent of A. So it's part of the whole. The whole is the initial concentration. The part is what's left over. Percentage remaining would be what's left over divided by what was started, the concentration that you started with. So we need to find the value of that fraction. Lucky for us, that fraction is part of the integrated rate law. Natural log of A at time t divided by natural log of A at time 0, or natural log of that fraction. There's only one natural log there. That is equal to negative K times t. So we don't need the individual value of A at time t in initial concentration. We just need to know what that fraction is equal to. And that's multiplied by 100% will tell us the percent remaining. So plugging in the values that we do have, plug in value for K, T is 25 minutes. So natural log of this fraction is equal to negative 0.2733. Got the fraction as part of a natural log. We want to get that out of the natural log, so we do the same thing as the last slide. Raise e to the power of both sides. That gets rid of natural log, and we just have that fraction left over on the left. So this ratio, concentration of A at time t divided by initial concentration, is equal to e to the power of negative 0.2733, which is 0.761. We multiply that by 100%. 76.1% remains. So after 25 minutes, no matter what concentration you start with, 76.1% of that initial concentration remains for this reaction. Any questions here? Anything unclear? Confusing? Nothing? We all got it? Ready to move on? Okay, we are moving on to 14.4. So this first section, we talked about a bunch of different factors that influence reaction rates. This last section that we just did is all about concentration of reactants. You decrease concentration, that will decrease reaction rate. Over time, reaction rate decreases because the concentration of reactants decrease. This section, we're talking about how temperature influences reaction rate. So that was one of the factors that influences reaction rate. You increase temperature, reaction rate increases. So we're going to understand why that is, and then other factors that determine the magnitude of the rate constant. So we'll talk about each of those. And to kind of set this up, we need to think about reaction coordinate diagrams. Reaction coordinate diagram, we have potential energy on the y-axis. So this diagram shows relative energies of reactants, products, and what we'll call that transition state. Transition state is the state of the reactants as they're forming products, which is bonds are breaking and bonds are forming. This is the high energy, it's always higher energy than reactants and products. And then the x-axis is just reaction progress. It's not time. Just as the reaction goes on, it will absorb energy to reach the transition state and then release energy as products are forming. So this transition state up here, this is high energy. This is always higher energy. Than reactants and products. And the amount of energy that's required for the reactants that start at a certain amount of energy, they need to reach the energy of the transition state. This is activation energy. This is E subscript A. Energy required to reach the transition state. This is activation energy. Energy required to activate those reactants, make them ready to form the products. For every reaction, energy is required to reach that transition state. I said that. This is always higher energy than the products, so there's always at least a little bit of energy required to get to that transition state. Breaking bonds requires energy, so that's what energy is required to get to the transition state. Forming bonds releases energy. So depending on the magnitude of how much energy is released compared to the amount of energy required, that determines if you have an exothermic or an endothermic reaction. The blue line over here, the products are a higher energy than the reactants. Delta H is greater than 0. There's a net absorption of energy. So the process, the reaction absorbs energy. This is an endothermic reaction. net absorption of energy. If the products release more energy when those bonds are formed, then the reactants required to break their own bonds, then this is an exothermic reaction, and energy is released. One thing we briefly talked about, this might have been in my 9 a.m. class, was about ATP. So you all learned breaking ATP bonds releases energy. But I just told you that breaking bonds require energy. So what's happening with ATP is when you break the bond in ATP, that requires energy for that bond to break. When that ATP bond is broken, you have your ADP and another molecule. The formation of those bonds in that other molecule releases a lot of energy. So it's actually the formation of that byproduct, a phosphate something, I don't remember what it is, that releases a lot of energy, and that's why we say ATP, breaking ATP bonds releases energy, but it's really not the breaking of the bond, it's the formation of something else. You don't need to know that, I don't think, for your biology class. Maybe you do. I don't know, I haven't taken biology in a long time. But just to clear that up for our class, and when you move forward, breaking bonds does always require energy. Forming bonds releases energy. So if there's a net release of energy, that is what we're talking about for ATP. Exothermic reaction, energy is released. All right, let's talk about a real reaction here. This is the decomposition of NO. I don't know if you remember, really early in 1070, we talked about different reaction types. It feels like forever ago. But decomposition was one of them. So we're starting with NO, nitrogen monoxide, and that reacts to form dinitrogen, N2, and dioxygen, O2. So we start with reactants, NO, that are at some energy level. As the reaction progresses, those reactants absorb energy, and the nitrogen to oxygen, those double bonds, they have to break. Energy is required to break those bonds. So it's absorbing energy to get to the transition state. Transition state is when bonds are breaking and bonds are starting to form. Bonds breaking requires energy. Bonds forming releases energy. So as those bonds start to form and the atoms are releasing energy, their energy decreases until they reach the products. So breaking this double bond here requires energy. And we've got 2 or 4 free atoms for this reaction here, some free nitrogen, some free oxygens. They come together and form the triple and double bonds that releases energy as those bonds are formed. And overall, this reaction is exothermic. Got our transition state. These are the products. And because the energy of the products is lower than the energy of the reactants, there's a net release of energy, exothermic reaction. Questions so far? Anything I can re-explain?
So, like, why is it exothermic at the bottom?
It's exothermic because the products here, remember the y-axis is energy. The products are at a lower energy than the reactants, so that means overall the net amount of energy decreases of these molecules, and so that means the energy was released. They lost energy, energy is released to the surroundings, so it's exothermic. Yeah.
If we can draw the graph and they just give us the decomposition of NO, do we have to know that's exothermic?
No, you'll either be told it's exo, told it's endothermic, or yeah, that you would have more directions.
Okay,
For sure.
thank you.
Yeah. Okay. Now this whole section is supposed to be about temperature. So why does temperature matter here? We're going to talk about collision theory in the next slide, but just still thinking about this reaction here. It absorbs these molecules absorb energy to break those bonds. For these new bonds to form, 2 nitrogen atoms have to collide. 2 oxygen atoms have to collide. That has to occur for those bonds to form. We can't have 2 atoms separated and then they form a super long bond, right? They have to get close to each other to share those electrons. So collision theory describes how reactions occur when reactants collide with each other, but only when they have the appropriate energy and are in the correct orientation. So let's talk about energy first. For 2 atoms to collide to form a new bond, they've got to collide with each other. If they have more energy, higher energy, they're moving around faster, there's a higher probability that they're going to collide. So this is where temperature comes in. If you increase the temperature, you're increasing the kinetic energy of those molecules. They're moving around faster, more likely that they will collide. So increasing temperature increases reaction rate. Not all reactions, but many reactions occur in a solution, which is what this picture is showing here. And so if you increase the temperature of the solution, you're increasing collisions, increasing the likelihood 2 atoms will collide with sufficient energy to then form their new bond and form the product. So that increases reaction rate. Increasing temperature increases reaction rate. There are some really slow reactions at room temperature, but if you add heat to that reaction, the reaction rate will increase. It'll be a faster reaction. Now this little bit about correct orientation. So these are the images mostly from the last slide. We have 2 NO molecules at the transition state. NO bonds are breaking. If the O2, the 2 oxygen atoms are lined up, they can form that new, or that's nitrogen, but they can form that new triple bond. Over here, if these atoms are lined up, they can form that new bond. Down here, we break this bond, break these bonds, then the nitrogen and oxygen are aligned with each other. The 2 oxygens are not lined up. 2 nitrogens are not lined up, so no reaction is occurring. Now molecules are constantly moving around. They do have to be in the correct orientation for those bonds to form. So if they're moving around faster, there's a higher likelihood that they'll end up being in the correct orientation. So molecules will continue moving around until they form their products. Okay. Question? Okay. We're going to end class here. This is where I ended for my morning class. So we will end here. This is the end of what will be on the midterm. We'll continue these notes on Monday, but you have everything you need to study for the midterm. Yeah. So what? Hi.
Question. So this isn't like direct